The science of chemistry has disappointed many people. It disappointed the emperor of China in the year 59 BC. He had been told that one of his court officials, Liu Xiang, could make gold. A great feast was organized, at the end of which Liu Xiang was to prepare a small quantity of the precious metal. After toiling away with complicated apparatus for several hours, all he succeeded in producing was an unpleasant smell. Liu Xiang was executed on the spot. This true story reflects one of the problems which has confronted mankind since the dawn of civilization. The problem being understanding how substances change into different substances. This phenomenon of substances changing into different substances has now evolved into the grand science of chemistry. So what is chemistry? Chemistry is the science of substances and how they turn into different substances. And very frequently, we can recognize a chemical change because there is a change of color. As I pour my chemical water from one flask into another, you'll notice a color change. And this is because I am making a new substance on every occasion. Chemistry plays a hugely important role in our everyday lives. Masses of substances and materials that we use on an everyday basis owe their existence thanks to the science of chemistry. Plastics, polymers, dyestuffs, detergents, perfumes, toothpaste, pharmaceuticals, fuels, explosives, a whole range of remarkable substances. Tap water, fizzy drinking water, masses of substances, fertilizers, owe their existence thanks to the science of chemistry. Chemistry, the science of substances and how they turn into different substances. Now here I've showed you some experiments with chemical waters, and I've illustrated for you the principle of what chemistry is about, substances changing into different substances. I'm now going to move to a different type of water, which I have in my container here. This type of water, which is by magicians called magic disappearing water. I will pour some into my beaker here, and I will now throw it into the air and show how it disappears. And I will stand under it there, and don't look for it, you won't find it. And the reason is it has disappeared into thin air. Why has it disappeared into thin air? Because that is what it is made of. This liquid which I have here represents one of the greatest triumphs of the science of physics. Physics is the science of matter and energy, and one of the greatest challenges of the science of physics in the 19th century was to be able to achieve temperatures which are low enough to turn the gases of air into liquids. And what I've got here is liquid nitrogen, and the liquid nitrogen has a boiling point of minus 196 degrees centigrade. Now, as you see, it's boiling away in my plastic bottle here, and the reason why it's boiling away is because this room is remarkably hot compared to the temperature of the liquid nitrogen. We here are at about 21, 22 degrees centigrade. Liquid nitrogen has a boiling point of minus 196, which is almost as cold as you can get anywhere in the universe. Absolute zero, the coldest temperature in the universe, attainable theoretically, is minus 273 degrees centigrade. Now, one of the golden rules when you have liquids which are boiling is never ever put them into containers which are tightly sealed. Well, that's precisely what I'm going to do now. I'm now going to have these Sprite bottles here, and I'm going to tightly put the stoppers on, and I'm going to gradually put them into these dustbins here. Now, the reason why you should never ever do this is because when liquids boil, they undergo a huge coefficient of expansion by a factor of about 800. I have poured in approximately 100 centimeters cubed of liquid nitrogen into each of these bottles, and that 100 centimeters cubed will expand into about 80 liters. Now, these bottles have a volume of 0.5 of a liter, and therefore, when that liquid nitrogen evaporates, it will occupy about 80 liters. It will generate a pressure of about 160 atmospheres. Now, these bottles, very clever though they are, made of brilliant polymers, they will just simply not withstand that pressure, and therefore they may explode. They don't always explode, but when they do explode, the noise is really quite substantial, and that's why, for safety reasons, I have put them into the bins. Now, that will continue to boil away. You may hear very loud bangs, so please be warned, but in the meantime, I'd like to show a couple of fairly obvious experiments with liquid nitrogen. The most obvious one being, of course, is to freeze some water. Water freezes at 0 degrees centigrade, and I will pour a small quantity of water into here and cover it with liquid nitrogen. So there goes our water there, and I shall now pour liquid nitrogen on it, and that will obviously turn the water into ice. Now, unlike the experiments which I did with my chemical waters, when I mixed chemical waters which were colorless together, and you saw a color change because a new substance was being made, here we have a totally different type of effect. You see, there is no color change at all. And that is because here we have a physical effect. The two colorless liquids, which I have mixed together, are now changing their state. They're changing, one of them is changing from the liquid state to the solid state, that is the water, and the other one, the nitrogen, liquid nitrogen, is turning from the liquid state to the gaseous state. So here we have the three states of matter in one very straightforward experiment. Now, as the liquid nitrogen continues to boil away, you may hear a slight crackling sound. Now, this is because when water freezes, it expands slightly, and as it expands, the crystals take up a greater area, and they push, a volume, should I say, and they push against one another, and sometimes this may lead, it sets up enormous mechanical forces, which is what the crackling is about, and sometimes the beaker may actually crack. So we shall keep our eyes on this, allow the process to continue, and I can just hear the beginnings of a crackling sound. Now, just top it up, make sure we continue to freeze our water. And I wanted to tell you that when liquid nitrogen was first made at the end of the 19th century, it did set off an entirely new era in the history of technology, and that's liquid gas technology. And thanks to that, today we have frozen food, we have a huge number of all sorts of effects that we benefit from. Among them, of course, are refrigerators. Now, to continue then on our experiments, and also the science of cryogenics. To continue with our experiments with low temperatures, these, by the way, approximately 5 to 6 minutes, you'll hear the bangs, so please be warned. I'm now going to show you an experiment with a solid. Here we have a piece of rubber tubing, and it's elastic. The reason why it's elastic is because when you stretch it, it returns back to its original shape. Now, the reason why it's elastic is because I can hear the pressure being taken up, so you may hear a bang shortly. Now, the reason why it's elastic from a thermodynamic point of view is because it's very warm in here. And because it's very warm in here, these molecules in here have lots of energy. However, I will now place the rubber tubing into liquid nitrogen, and please observe carefully what happens as we lower the temperature. And you'll notice this most interesting effect, you see, of a shower which is issuing from the end of the rubber tube. Now, why does this happen? Well, it's for the same reason that the bottles are exploding in there. And that is because as the liquid nitrogen boils fiercely when it comes into contact with the very hot rubber tubing, so it expands enormously, as I said, by a factor of about 800. That boiling, therefore, pushes the liquid nitrogen out, setting up a pressure that forces it out there. As you saw there, we didn't have anywhere to escape, and that's why the bottle finally gave way. Now let us inspect our rubber tubing, which we have here, and let us see what has happened to the elastic property. It went in as an elastic solid, but now you see it's no longer elastic. And if I whack it one on this table, please watch carefully, then it will shatter into 1,000 fragments. Now, the reason why it shatters into 1,000 fragments is because at high temperatures, the molecules are all vibrating. We have lots of energy. The molecules of the rubber tubing have lots of energy, so they're all going around like that. But when you drop them into liquid nitrogen, there is very little energy, and so the molecules suddenly freeze. They go like this. They freeze solid. I'm, of course, being silly, but I'm illustrating an important scientific principle. Now, I wanted just to show you here, we're just going to see, in the meantime, I just wanted to show you our beaker has indeed cracked. There it is. There's a piece of glass has fallen away from it. And what that shows you is, it just shows you the huge forces, intermolecular forces, which are set up when water freezes. It freezes, the molecules rearrange themselves to form an open lattice. Now, here I have a beautiful balloon, and why does it have the pressure? It has pressure inside it because the molecules of nitrogen and oxygen in the air are moving around because they have lots of energy, because it's very warm. But if we reduce the energy by pouring liquid nitrogen over the balloon, then you will notice a very, very interesting effect. So please watch carefully. I'm going to pour liquid nitrogen over the balloon, and as you notice, the balloon starts to contract. And as the balloon starts to contract, so you'll notice getting smaller and smaller, and it takes a very, very a shape which has there's no elasticity. It has completely collapsed. Now, why is this? Well, once again, it's the same reason. At the low temperatures, sorry, I think the floor's cracking underneath me. So everything's freezing all around, but we're still all right. Please look carefully. The balloon has now collapsed. It looks very sorry for itself. But if we allow it to warm up a little bit by shaking it up, throwing it up in the air in a very short space of time, let's see if I can catch it. I'm sorry, it's escaping from me. It's escaping. As you see, it has been restored to its full shape. Now, why is that? Because at the warmer temperatures, the molecules have more energy, and therefore they move faster and move more rapidly. Now, let's just carry on to my favorite topic, which is fire. This flame here represents one of the greatest traditions of the human race, and that is, of course, our ability to make fire. We know that in East Africa, where the first ancient civilizations were 100,000 years ago, people were able to make a fire and sustain a flame. I'm now going to just show you how 10,000 years ago, for thousands of years, flames burnt like this. This is a piece of cotton wool, and you'll notice it's a dreadfully boring flame. It just burns like this. Why is that? Well, because the cotton wool is surrounded by air. Air only contains 20% oxygen. It was only realized that air is a mixture of gases about 300 years ago, and we've been on this planet for 100,000. And once chemists had discovered the oxygen is the vital component of air that makes things burn better, they started either combining fuels with oxygen or mixing them with oxygen. And here I've got a piece of cotton wool which has been chemically combined with oxygen. Please watch how differently this burns. And we put it in here. How'd you notice? And it's blown the flame out. I knew it would blow the flame out. Damn it. That's adding an extra 3 seconds onto my talk. Never mind. We shall quickly. I was ready. I had my matches. Now, what I wanted to show you, I've just shown you the world's first high explosive nitrocellulose or gun cotton. I would love to do an explosion with it, but I can't. We don't have the time, so I'm going to show you a propulsion. This here is a mortar. It's a type of device which is used for propelling fireworks high into the sky. I'm not going to prepare fireworks. I'm going to propel ping pong balls. So sorry, I got 4 ping pong balls in my pocket here. I have a cage, gun cotton cage here, dropping it to the bottom. Sorry. Has it gone to the bottom? I don't know. Too bad. I'm going to force it to the bottom. I'm sorry, I'm struggling a bit against odds and against time. Let me just... There we are. I think it's gone to the bottom. If it hasn't, too bad. We're going to shove a fuse in there, and that will hopefully, when this goes off, we'll see it going up to we'll watch the ping pong balls fly out if they manage to reach the bottom. If they didn't, that's too bad. We won't see anything. But nevertheless, there goes our fuse. Hopefully, come on, catch fire. Time's running short. Dear me, this is a very bad piece of fuse. So I'm going to have to put my fingers on the lift, and there we go. Now, on to the final things here. Here we have, there we are. I don't know whether they went, did anything happen? Yes, they walked out. Now, here we have, sorry, very quickly, we have here a balloon filled with hydrogen, caused a complete sensation among scientists. The lightest gas in the universe going off there. That's pure hydrogen. This is thunder air, aria tonante, a mixture of hydrogen and oxygen, and that goes like that much louder. Now, for my very fine work, I have here a mixture of hydrogen and oxygen. I have a fuse which I'm going to make here, and this will be my final experiment. We're going to have a thunder and lightning effect here. We're going to have a thunder lightning. Sorry, everything is going mad. Let's just get rid of this balloon. It's getting in my way. Now, here we are. I'm going to make up some flash powder, fuse powder. This is going to be, so to summarize, what have I been talking about? Chemistry. What have I been selling to you? Chemistry. In simple and direct language, chemistry for all. So here we go, fingers crossed, and there it is. So thank you very much indeed. I wish you all the very best. Thank you for your kind attention. Thank you very much indeed. Thank you so much. I did 15 seconds on the dot. We're still in one piece. I wish you very, very best. Very, very many thanks indeed. Thanks.